Yeah. Hello, hello, hello. This is Twitch Stream Thursday. My name is Mofi, and I'm here with Nick.
I'm Nick.
Yeah. So today, Nick, what are we going to talk about today?
All right, so today we're going to be talking more about AI. And so just a quick recap of what we did last week, or the week before last week. We showed you how to build a neural net.
Yes.
And how it works.
Well, not.
Well, how it works, but not how we actually got to it with all the weight values.
Right.
So we built our own neural network, and it worked. You gave it some numbers, it gave you an output, but I gave you hard-coded weights. So today I'm going to try and show you how to actually get those weights.
Okay.
So first things first. I'll draw a nice little network here. So this is our Fahrenheit graph right here. So we have our input node and our output node, and then we have our bias node right here. And our bias node, as you notice, it's always 1.
Mm-hmm.
And our input node is affiliated with this weight 1, and our bias node is affiliated with this bias 1, which is just the weight for the bias. And so in our ideal Fahrenheit or Celsius to Fahrenheit converter, our weight 1 will be 1.8, and our bias 1 will be 32.
Right, and we know this weight and bias to be that because literally the formula of conversion is this. So then when we build a model, we expect like our model to somehow get to this.
Converge to this point, to these values.
Okay.
And so we're going to show you how, I'm going to show you how to actually train this to get these values. So when we put this 30 in, it gets multiplied by 1.8 plus the bias times 32. So that will give us 86 degrees Fahrenheit. So put in 30, we get 86 back. So this right here is our expected value. We're expected to get 86. So when we train our neural network, we have this sort of expected value for this input. And this is when we're doing supervised learning. So with supervised learning, we have a set of inputs and an expected output.
Okay.
So 30 is our input, and 86 is our expected output. And so to go a little bit further, when we initialize our neural network, like in the computer, it'll look something like this. We'll set up that we have this. We'll have our input node, and the weight 1 will be initialized to something random. So let's say 0.2, and that goes to our output.
So that 0.2 could be any number, actually.
Right.
Okay.
Yeah, so that's just completely random. It'll be different every single time you start training your model. It'll randomize it to something.
Okay.
So we're just doing 0.2. It could be 1.3, 99, sky's the limit. And then our bias is normally initialized to 0.
Okay.
And then so if we put in 30 here, and then we end up with 30 times 0.2.
That's 6. Wait, is it? Yeah, it's 6.
Okay, plus 1 times 0. So that would be 6.
Yeah.
I trust your math.
Yeah.
My math is horrible.
Yeah, I mean 30 times 2 is 60 and 0.2, so I'll divide by 10.
So we put this input 30, and we're expecting 86.
Okay.
But our output value is actually 6.
Right.
So what we need to do is kind of tell the network, how bad it's doing. And
so when you say we need to tell it, the network doesn't really know the expected output, or we tell it that from outside?
We well, we're kind of telling it, but we're telling it. We could just say like you're 80 off, you know, or like we need to give it a way to gauge how far its value is to the expected value.
Okay.
So we call this function like the cost function. And when we trained this model in code in the previous example with Keras, we used what's called the mean squared error, and that was our cost function or our loss. I never really talked about it too much.
We just had a bunch of weight numbers.
So that's something that you have to define when you're training, and we just used mean square error as our cost function. So to show you what that function looks like, it's pretty much just you're taking the your target, your expected value of 86, you're subtracting it by your actual output, and then you're squaring that.
Okay.
So this is like the cost.
6,400.
Good.
It's 8 squared.
True. Again.
1 0. One more zero.
Again, I'm extremely horrible at math. So if you're following along and you're like, I'm really bad at math, I don't think I can learn neural network stuff.
Right.
I'm the worst at math.
So he's the one bad at math, and he's better at AI. So you figure.
Okay. So yeah, we end up with this cost of 6,400, and our goal is to minimize this number. We want this to be as small as possible.
Right.
So if we ended up with 86 here, this would end up being 0.
Right.
Does my math check out?
No, you're good. You're good. that does check out.
So once we get this value, we want a way we need to update these weights. We in a bigger graph, we'll go over next week how to do a bigger graph. This is a very simple graph, so we're going to start here. We have this 30. We can't manually change this 30 because that's our input, and it's going to be similar when we have hidden layers in between. We can't really change those. The only thing we're changing are the actual weights.
So another thing, so if you just had, so let's say I'm the neural network, and my job is to like minimize this number, and I only have one input, and I want to make it 86. And I just chose randomly 0.2. Now I have an option of changing that 0.2 or the bias. Like if right now, the easiest thing for the neural network to do is just add the bias as 80, and I'm at the right answer.
Right. Exactly. So that's what we're going to talk about. How the network knows which weights to nudge.
Okay.
And I'm gonna do like a nice little graph in code in a second. But so we have this cost function, and we're trying to minimize the cost function. So in order to do that, let's make a function in respect to all of the weights, and then the cost. So say we have this cost, and then we have the expected. And that's going to be a fixed number.
Okay.
So that's 86 in this example. So 86. And then we have this actual output. And we calculated this by 30 times the weight 1 plus 1 times the bias. So let's just fill that in here. So we have 30. That's going to be fixed. Times weight 1 plus 1 times bias 1 squared. So this is our cost for this this one example, this 86 and 30. And we can plot this in a graph.
Right.
And our goal is to find the minimum of that graph.
So you're plotting this graph by changing what variable exactly?
So everything in
W1
here,
and B1?
Yeah, so everything in here is a fixed number except for W1 and B1. So we can call that X and Y, and then our cost would be Z.
Okay.
So if we open up
cost graph?
Yeah, cost graph.
Okay.
And let's scroll down to the bottom to make sure I have the right things commented. Comment that first back in, and then comment that one out, and then save it.
So this is doing some CMAP stuff. It's doing a scatter plot. It cost 1, 2.
Most of these are things that aren't going to get graphed yet.
Okay.
But
all right. So I'm going to do Python cost graph.py.
So what this is graphing is graphing this function right here for this 1 point. So as you can see, it's pretty easy to tell like where the minimum here is on or which axis. Okay, so this is the weight axis.
Okay.
I think probably. And as you can see here, it's pretty flat, so we can't really find a minimum there. It could be anything in either direction.
Right.
But then if we go here, you can kind of see a very tiny kind of curve to it.
Right.
Right. So like,
what axis was that?
This is I think this one is the bias.
Oh, okay.
So we're able to find this sort of minimum right here. And if you like do kind of like right here, this is like the actual minimum we're finding. And then anywhere along that plane,
that line.
Yeah, that line in there would probably all be the same cost. And so if we do look at this like this, we only have this one example, and we have 2 unknown variables.
Okay.
So most of the time, whenever you have 2 unknowns, you need at least 2 equations.
Yes.
Right? Yeah. So we can solve this for many values, and if we pick any of these values, it'll all come out the same with this 30 and 86. But if we put something else in, it might not be the same.
Right, because like if you want to make 86 out of 2 variables, you have like a lot of combination of it, right? Okay.
So what we need to do is we need to give more examples.
Right.
So let's do another. So this is cost 1. We have, let's say, cost 2, and let's do 15 Celsius, which I think is 59 degrees Fahrenheit.
Okay.
So our expected is going to be 59. And then we're going to subtract, our input is 15 times weight 1 plus 1 times bias 1. And now we have 2 equations, which we should be able to find the min, but let's just do 3 examples. So here we have cost 3, and let's do negative 10 degrees Celsius, and that's 14 degrees Fahrenheit. So 14 minus our input of negative 10 times weight 1 plus 1 times our first bias.
So like now with this 3 equation, and to solve for W1 and B1.
Right, but what we're going to do is our actual cost is we're going to add them all up. So cost 1 plus cost 2, cost 3, and just take the average of that.
Okay.
And that's going to be our total cost across all of these training examples. And if you go back to the code.
Yeah. So that's I think what you're doing. You have x1, that is the negative 10 degrees, and target is what is the expected output is.
Right.
Okay. And y1 is the total cost, I'm guessing?
No. Y1 is this.
Oh no, y1 is one of the, right? Just
right.
like
X. So on this is the y1.
Right.
This is the output.
Gotcha. So the cost, okay. All right, you have 3 costs, and then you count the total cost. So I'm guessing you want the second.
Are people seeing this graph?
Yes.
Okay.
Yeah.
Cool.
Screen is being shared. Mistake made once, not every time, Nick. Okay.
Okay, so now this is showing the average cost across all three.
I'm going to actually close this so that I have a little bit more screen real estate and probably drop down one font size so that, yeah, I can just show the entire line here. So I'm just doing the plot again, but this time instead of doing just cost, I'm plotting against the entire cost and taking the average of it.
Yeah, it's just the average. So summing them all up, dividing it by 3 because there's 3 costs.
Right. And we want to then minimize this cost as low as possible by switching these 2 variables. Right. Okay. So if I do this time.
So now if you move it around, you can see there's like a clear minimum across all of it.
And what is that value?
That red dot is the 1.8 and 32 for the bias.
How do you find that?
I'm just plotting that value as a default. If you go back to the code, I'm just plotting 1.8 and 32 as a red dot because that's what we're expecting to get to as our minimum. And if you look on the graph, that's like kind of like the lowest point in the
yeah, no, I can. Yeah, so I was like hoping I could see it from the graph, like directly. I see the red dot is the lowest, but I'm like in a 3D plane, I'm trying to hover my mouse over, so it's not working out as expected. But no, I think we're going pretty close. But yeah, no, okay. So now the next question would be: so see, this is a pretty simple example, right? This is a pretty like I think even with 2 things, like even with 2 inputs, we could have like reached this conclusion, right? Even if you didn't have, let's say, I get rid of cost 3 and divide this by 2, right? I still expect this to get to where it is going right now because I have 2 variables and 2 unknowns.
Yes, it should still be a pretty clear minimum.
Yeah. So right, but does this mean when we have, let's say, like imagine this image right here in the background.
So, as you can see here, we have like a bunch of ways. So, this Fahrenheit to Celsius example is a really easy way to show how we're trying to get to the bottom of the cost function, just because there's 2 variables. So that gives us 3 dimensions that we can look at pretty easily. However, when we're looking at something like this is like 1, 2, 3, 4. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 26.
And
26
plus biases between each hidden layer, right? We have 1, 2, 3 biases.
Right. So we're going to have like 30, 40 dimensions.
Right.
And that, how you even plot a 46 dimension graph. Like, can you find the minimum of 46 dimensional function easily?
Well, I can, but.
Right. So we can't actually just find that like minimum value just by like looking at it like we can in this example. So we actually have to find a better approach to get to that minimum.
Okay.
So I'm going to simplify this cost function even more. So we have.
Give it 1 second. Okay, we're good.
We're good?
Yeah.
Cool.
I just switched to the full screen so that you could show this.
Okay, so I'm going to draw an even more simplified cost function.
Okay.
So let's just have like this nice parabola. And then to us, the hopefully obvious minimum of this function is right here.
Right. I mean, if you're this lucky to get a function this nice.
Right. So, how do I get more colors? Ooh, fancy.
Any color you want.
So let's say we start out right here, right?
Right.
So I don't know how much Mr. Math Man.
I think I like just by looking at the picture I can predict what you're gonna say next. I think you were bringing up the C word, which is the calculus.
Right. So
last time I took calculus was what 5 years ago, 4 years ago.
Right.
So yeah,
we're trying to find our way to this blue dot, and we're here this little red dot, and I'm gonna get another color.
And I think I'm gonna name drop here those of my math fans out there. I think you're trying to find the local minimum.
Yeah. So
something.
In order to find that, we're gonna take this point right here.
I think yellow is not the best color.
That's not a good color. I'm just gonna keep red.
Or purple.
It can look up here, look down here, and it can decide which way it wants to go.
Right.
And like if we look at this line right here that it's on, as you might notice, like a slope, or
yes.
like how steep. We can figure out the steepness of this point and go down in the opposite direction, and that'll help us find the minimum point.
Yeah.
Right. And then so for those of you that have seen things like this before, we can take the derivative of this function. So the derivative of this function, we'll draw another graph. So the slope here is pretty negative, and then it's positive.
So you want to just like find the point where it's the lowest.
Right. So the slope of this line will look something like this, and right here being our minimum value is 0. So our goal, we want to let me switch to highlighter. We want to minimize this cost, and the best way to minimize the cost is to look at both of these values and decide how much we want to adjust them. Okay. And the way we can decide how to adjust them is how the change of this one value affects the cost.
Okay.
And so as you can see here, like if we're not looking at these, change this color too. If we're not looking at the inputs and we just look at these weights, we have full control of the weights. So you could change them however much you want, and they'll both kind of affect this output node the same. So can you tell me something on this graph right here that makes a difference on how this weight would affect the output? Does that make sense?
Repeat the question.
So if we look at these weights, we can change them to anything we want.
Right.
And if we're not thinking about the inputs, then they both kind of affect the output equally.
Right.
So if we are thinking about the weights, how can we tell which weight will affect the output more? If that makes sense.
Well, if I just know the input what they are, right? I know that one of the input is much bigger. Like if you're considering both as inputs, bias is 1, one of them is 30. So change in W obviously is going to be much bigger than change in B1.
Right.
Okay.
Yeah. So cool. that's we want to look at these inputs, and that's like the whole kind of idea of backpropagation is we have this output. We want to figure out how much which weight to edit so that we're like editing it in the most optimal way, not just randomly moving them up and down. We want to figure out which one will actually affect it more, and we can go backwards and see the previous node and see that this is 30. This is going to have a lot larger of an effect on the output if we change this W than if we change this one with 1. Okay, so if I
change the color,
okay, and then probably go back to pen. So I'm just going to draw the graph again.
You just copied it from there.
Oh, it's okay. Gotta get this good muscle memory. Start drawing really good graphs. Okay, so we have these weights and biases, and this cost function. So let's just write the cost function here. So we want the target minus.
Oh, sorry. So target minus you do the whatever you found. So weight 1 times input plus.
Yeah, I was just saying the output. for now.
Well, no. You looked at me like I should give you more than just like just one.
But you're
more.
exactly right. But I'm not going to write all that down.
Okay, cool.
Because I'm lazy. So we have this cost function. And we have a weight. And we have a bias weight.
All right.
And we want to find, for those of you who know calculus and stuff, I'm going to try to make this as least calculus-y as possible. We want to find the change in the cost function.
He says he wants to make it least calculus and start literally with like the most calculus-y symbol possible. But that's besides the point. It's okay. The difference, change. You got it. I think most people, our viewers are.
We want to find the change in the cost function. So let me just write cost with respect to change. We're going to first look at this weight one with respect to change in weight one.
Okay.
And to figure out this change, we're going to be doing derivatives. So it is going to get mathy for a few seconds, but you're allowed to just glaze over this part. We're gonna come up with like a little equation, but for those of you who actually care about where we're getting this equation, feel free to keep watching.
Viewer discretion advised.
Yeah.
If you
rated M for mature. So we can use the chain rule, to help us figure this out. So I'm going to rewrite it over here just because I'm running out of room. So you have the change.
Again, you can always move these things
in this cost function, and I'm actually going to write out the cost function this time in full.
All right.
So we have the target minus this output, which would be the input times weight one plus, I'll put this in parentheses, plus,
if you want to just move it, just like,
I'll just erase this.
Okay.
We're doing this all over again.
Cool.
So input times the first weight plus 1 times the bias.
Okay.
And then we're squaring all this.
Yeah.
Cool. All right. So we want to find the change in this cost function with respect to the change in weight one. But in order to get there, we're going to first do it in respect to the change in input times weight 1 plus 1 times bias 1. So we're doing the change in the cost in respect to the change in this output right here.
Okay.
I guess I shouldn't just hover over and gesture things. I should highlight them. So this output before we calculate the cost. And thank you. Okay. So, and then we want to multiply this by this thing I'm going to write on this next line, just because I'm way out of room. The change in this input times weight 1 plus 1 times E1 for the bias in respect to this weight 1. And then, so if you multiply these together with your standard, arithmetic, these two changes cancel each other out.
Okay.
So let me highlight those. So this and this cancel each other out. So then you end up with, actually, I forgot to write. I'll write it after. So then you end up with the change of the cost in respect to the change of this weight 1.
Okay. So this is a change of weight 1, not just weight 1.
Right. I just I want to erase these before I write this. So I don't have to rewrite this again. So yeah, the change in weight 1. Because that's what we want to figure out. We want to see how much this changing this will affect our cost function.
Right.
So these changes will cancel each other out.
Right.
But figuring out the derivative of this is a little complicated, so that's why we're using the chain rule, because these two functions are easier to solve for. So I'm gonna make another page. Okay, so if we do the change in the cost versus the change in the input, how this works is we substitute this value here into here, and we treat it as x. So we can rewrite this whole thing as we want to find the derivative of the target minus x squared.
So x would be replaced with this whole output that we were getting before.
Right.
Okay.
And then if we take the derivative of that, we get 2 times the target minus x. And then we need to multiply it by 1 because we first do if you are familiar with derivatives, you multiply it by 2 for it's 2 minus 1, so power becomes 1. And then we need to multiply it by the derivative of this inside, which target is just a constant, so that becomes 1. And then
shouldn't it be negative 1?
Yes.
Okay.
But I think it ends up we don't care about that because we want the negative of the cost function. So it's negative, so on. So we end up with 2 times the target minus x as this first value, and then we need to multiply it by this second value, which, so we've replaced this whole, that's highlighted, we're going to replace this with this part and substituting W1 for x. So we're going to have input times x plus 1 times b1, and the derivative of that, this is a constant, so it goes away, and we just end up with x going away,
just input.
So input. So the total derivative ends up being 2 times the target minus output times the input. So that's our cost function.
Okay.
Or not our cost function, but this is how we figure out what we're going to do with the weight.
Right.
So we're just going to add this value to the weight that we have, and that'll proportionately affect that weight. So if W1 changes the cost function a lot,
right,
this value will be larger.
Okay.
And if it doesn't affect it that much, it'll be smaller. So we end up, if W1 affects it more, the number will be large, so we'll be adding a much larger value to it, versus this will be a smaller value to it, depending. And then, how are we doing on time? How much?
What, like 10 minutes?
10 minutes more? Okay.
10 minutes more.
Cool.
I mean, again, like our streams tend to get really long, and these are pretty heavy content, so I don't really want our viewers to like feel a lot more content. A lot of people actually watch it afterwards on YouTube later, so like we don't want to make the video too long.
Right. Yeah. So I should be. We're getting close. To
okay. Cool.
So we have this function right here, and what we're going to do is a lot of the times we're going to multiply it by a learning rate.
Okay.
And this learning rate is something that we choose, because if the learning rate is too large, we're going to overstep the minimum.
Okay. So
if you still have that graph.
Yeah, you drew it.
Oh yeah, this graph. I meant the other one, but this.
Oh, okay, other one I can get to it.
This is good. This is good.
Actually, I have it right here.
Okay, so if we just put this in like a view like this. So let's say we're right here.
Okay.
If our learning rate is too big, we might step over to here, and we've missed it, and then it's probably going to be just as big of a step because the slope here is the same as the slope here. So we're going to end up jumping back to the other side again, and we're just never going to hit the minimum.
Right.
So we want to scale it by a number, and this is just something that you just kind of have to play around with. So there's these things that are starting to accumulate with things in these neural networks that you just kind of have to play around with. And so far we've come across the different activation functions you can use.
Yeah.
How many hidden layers you want to use, how many nodes in each hidden layer, and now learning rate is another one of these.
Okay.
So we're going to use a learning rate of 0.01.
0.01?
Yeah, 0.01.
So 1/1000. Okay.
Yeah. So we're just going to multiply that by this value that we get.
So basically, another thing that probably could happen by looking at it, if you were to choose learning rate to be too small, you might end up like just taking forever to reach the thing.
Right. Yeah. So the smaller learning rate you have, the less chance you have of passing things up, but it could take a really, really long time. You might never get there just because it's so slow. With this Celsius Fahrenheit example, this 0.01 has been pretty decent.
So again, I don't really have any perspective on what this number, like what is it like a good average number for anything that things you have built or used before?
So again, we're gonna talk about some other things. Like this is just using like pure gradient descent, which you have one learning rate and it's the same throughout. There's other optimizers that they change the rate of the learning rate as training goes on. So it depends on what optimizer you're using. You normally have something like under 1 though. It's like normally 0.01 or 0.001 or 0.0001.
Because I think the last week when we were looking at the Google the TensorFlow thing, they had a thing like a 0.03, 0.01. Was it the same thing?
Yeah, that's probably the learning rate. And
okay.
Previously, when we trained the Celsius model, we used 0.01, I think, but we're using Atom Optimizer, which it changes the rate as it goes on, so we didn't end up missing things.
Okay, cool.
So I want to walk through an example. This might take time. But I think it's better to just do it now than wait till next week. I think
it's worth it.
If we get through all this, it's going to take some time, but you'll feel better in the end.
Okay.
If you hang through, stick tight. So this equation, we don't have to ever do these derivatives again. We can just use this equation that we got. I just wanted to show like why.
I appreciate it. Cool. No, I think a lot of times AI has a lot of magicy things people just drop in. Right. So I think looking where it came from definitely helps.
And if it doesn't make 100% sense, it's okay. You'll still be okay.
Okay.
All right. So let's go back to this example where we have our Celsius classifier. If you open up the code,
okay.
And can you open up the file
Backpropagation?
Yeah. Okay. So I have a model here with our values that we were using earlier, and it's going to train it and print out the weights at each step. So it's going to start off and print the initial weights and then the weights after one update, and every epoch after that. And I think I did 10, but let's just do 1.
So 1 would be just the initial step and nothing else.
It'll print out the initial weights and then it'll do 1 learning step.
Okay.
And then
Oh.
Okay.
Did it do it?
Yeah. So our initial weights, our bias was 0, and we started it out with negative 0.3855 as our initial.
Is it going to be always that, or it's random?
It's just random.
So if I run it again, I should see something different.
Right.
Okay.
And then our first update, it updated the bias to 0.09 and the weight to 2.3.
Okay.
And so as you see, it took a larger step here than it did with the bias because the input number is larger. So,
okay.
So that's just a small example. And as you can see, we're still like fairly far away from the value we want. And that was after one round of what I'm going to show you how to do on paper in a second.
Okay.
And it takes about 5,000 of these rounds to get it to something that's close to 1.8 and 32. So we're not going to...
So what I'm hearing you say is that don't do it in paper.
Yeah, don't do the entire thing in paper.
Okay.
It's good to kind of, work through it like by hand to see what's actually going on. But yeah, you're not going to be able to figure out these weights just by like hand doing it over and over again. It's too much work. That's why we have this computer to do it.
Good.
But I'm going to use these initial weights that it gave us and the first step so that we can check to see that we did it exactly what it was doing.
Okay.
Okay.
And here we're using, again, the Keras library, right?
Right.
And we're using the mean squared error. That's the same error we've been getting, right?
And then the... things backwards. So yeah, we're doing the stochastic gradient descent. Learning rates is 0.00.
That's the one we were initially looking at as well. Okay, all right. So onward.
So yeah, so we should get this exact value whenever. So I'm going to write that down before you change this, and then you can change it back to our view. So our first weight is 0.485. Let's just do
3.58, or like 0.486. You have to.
Fine. And then our bias is 0. All right, you can switch it back to my screen now.
Okay, there you go.
Okay, so now we have this this equation that we're going to use to actually update our weights, and it's learning rate times 2 times the target. I'm just going to call the output y.
Okay. Times input.
Times the input, which depends on which weight you're using. Does that make sense?
The input is like the 3 inputs we had, right? Like in the example. Why would that depend? Like the X train is the one we're calling our input, no?
Right. So it'll be this one, then this one, then this one.
Yeah.
But then sometimes if you have more than one node, it's all of those.
Right.
So we cycle through them. But yeah, so in this case, messed up. This entire thing is I. Sorry. Did it crash?
Probably. Hold on, we can connect back. Not a big deal. Okay. Here you go. We're back.
Okay, yeah. So both of these nodes are considered I.
Okay.
So let's start with our first example. I'm going to change this to a smaller font because I'm probably going to have to write small. So we have an input of 30, and we expect to get 86 back.
Right.
Okay. So we have our learning rate, 0.001, and we're going to multiply that by 2 times our output, or our target value,
86.
which is 86, minus our y, which is 30 times...
30 times 0.486.
I'm going to whip out my calculator.
Yeah, probably the right idea.
486 times 30.
Unless you want me to handle calculating so that you can
go
consider. Okay, so 14.58.
14.58. And then we're going to multiply that by our input, which is 30 for this weight. And don't have to calculate that yet.
No?
It'll be easier in a second. And then we have to calculate the same thing for our bias weight. So we have 0.001 times 2 times 86 minus 14.58, because our output is still the same. And this time we're multiplying it by 1 for our bias. So then if you calculate that, then you can just multiply that by 30.
Well, I already did it, so I can. So that one is 4.28. The top one. Yeah.
4.2852.
And just divide that by 30.
0.1428. Okay, so we have the values for one input. Then we have to do this again. We're going to do it with our 15. We expect to get 59. So 0.001 times 2 times 59 minus...
I can do that this way. 59 minus...
486 times...
486 times 15?
Yeah.
That is 7.29.
7.29 times 30.
I think this time is 15.
Oh, yes, you're right. Look at you. Smarty pants.
Well, I'm more excited about finding a mistake than anything else right now. So I'm motivated.
Yes.
If you...
So 59 minus 7.29 times 1 for bias.
Minus 7.29. Okay, so 50, then times 2 times 0.001. So that one is, the bottom one is 0.10342. Okay. And times that by 30 is 3.10.
15.
Hold on, divide that by 2. 1.5513.
1.5513.
There you go.
Okay, and then we need more. Okay, so then we have...
Minus 10, right?
Yes.
Okay.
So I guess I'll just do it on this new page. So minus 10, and we're expecting 14. So again, we have 0.01 times 2 times negative 10.
No, I think it's output, so 14.
Oh my god. Thank you.
It's good that there's 2 of us here.
Yeah, so 14 minus here, so 486.
So 0.486 times
negative 10.
Just do 10, negative 4.86.
So negative 4.86.
Right, so, okay, so 14 plus 4.86 times 2 times 0.001. Wait, am I doing it right? And hold on, let me do it again. 14 plus 4.86 times that by 14 plus 4.86 times 2. That is wrong.
You have to multiply by 0.9.
Right. So 14 plus 4.86. Okay. That times 2 is this. That times 0.001 is this.
0.03772.
And then it's going to be like point. There's going to be negative 0.3772.
Negative point. Are you sure? Yeah.
0.3772.
Okay. So this is our first epoch. We put through all of our training values.
Right.
We calculated this change, and now we actually need to update our weights.
Okay.
So to figure out our new weight 1, we want to add this, and this together, because those are all the things that we used to calculate for the weight 1. And then for the bias, we need to add this, and this.
Okay.
So I'm going to do the sum in green for the weights. So can you add all of these together?
Yeah, so what is the number? Okay. So see, 4.2852 plus 1.5513.
Yep.
Plus
minus.
Okay, so minus 0.3772, 5.4593.
Okay, so for the weight 1 it's 5.4593, and we're going to divide that by 3 because there's 3 of them to get the average.
1.81.
1.8197, blah blah blah.
And just like label that W1 if you want.
W1, but we're going to add that to W1 to get the new W1.
So our initial W1 was 0.486, right?
Yep.
So 0.486, 2.3058.
So 2.3058. And then if we look at, let's see if we got weight 1 right. 2.3, yeah. Look at that. Okay, now let's do the bias. So can you add up all of these in red?
Yes, so they are 0.1428 plus 0.10342 plus 0.03772. And divide that by...
Well, let me write that down first.
0.28394.
Divided by 3.
I divided by 3 too.
Yep.
0.0946.
0.0946 plus bias 1
was 0.
So then we get 0.0946. Hopefully. Woo! Yeah, we did our first epoch, and then we just have to keep doing that 5,000 times.
Yeah. Okay.
So,
like, where did you come up with this, like, 5,000 number?
I just, you keep bumping it up until you
so, like, what if you do, like, 7,000 times? What happens? Does it just start degrading?
No, it normally just starts to
like just jitter on the...
If you're... So, for this model that we're fitting right now, it's kind of impossible for us to overfit it.
Yeah.
But sometimes, if you're training and you don't have good data, and in some scenarios, the model isn't exactly what you need it to be. There's like a lot more layers and stuff. Then training it for more epochs sometimes can lead to like overfitting.
Okay.
But in this scenario, I don't think it's possible for us to overfit. So the last thing we want to look at is this gradient descent file. And this is just a nice graph to show like so when you're training it prints out like this this loss function value, and that's our cost.
Right.
So when you train it for 5,000 epochs, you can see the cost go all the way down to like 0.00. And then that's when our weights end up being like this 32 and 1.8. So in this, I'm gonna like print out the loss, the cost function, and the values of the weights and biases in a 3D graph. And so starting out, I'm going to use an even smaller learning rate.
Okay. And
20,000 epochs.
Is it not going to take forever to happen?
It'll take some time. Do you want to run it?
Yeah. Oh boy. Things are happening.
Yeah. It'll probably take some time, but you see it's slowly, the loss is working way down to 0.
So again, this is a pretty like a stable graph, right? It's like a low, so we can always see it's going down, but in real life, you could see something going down, going up, going down again.
Yeah.
Could happen, right? Okay. So by 20,000, does it go to 0?
It should get close-ish.
Oh man, 3.29.
Okay, so now we have our same cost function graph, and if you can kind of see, do you see this V in there?
Yeah, I mean I see it. I don't know if
your computer's freaking out because there's like 1 billion points being plotted.
Yeah.
But I plotted the value.
Oh, at the bottom we can see it pretty nicely. Like
it's very.
Hold on,
right
I got it. Hold on, let's stable down and slowly drag and push it up. Drag and push it up. See that? That's why you want your mouse to. It's going away. Anyway, so I can see the red lines, I think.
But yeah, so if we look here, you can kind of see the slope right there. It's a pretty small slope. But if we just wait and then tilt it up a little bit. Oh boy. Okay. It's kind of hard to see, but this is like a much steeper slope. So as you can see, it's like it started going here pretty heavily. And then when this slope started to even out, it started going inwards and follow that smaller slope.
Right. So maybe a better algorithm could have just, instead of taking this route, could have gone directly that way. Like, is it possible to go directly?
Right. But see, like the way that we're finding it is we're looking at the slope in the area, and we're moving it as a function of like how big that slope is. So the slope right here is really big, so we're taking larger steps in that direction, and the slope going towards the actual center is pretty small compared to that big slope.
Right.
So you're ending up taking larger steps there, smaller steps there.
Okay, so the lower hanging fruit, whatever is like bigger one closest to you. Okay.
We're still taking small steps in that direction, but we're taking much larger steps in the direction of the larger slope.
Right.
And that kind of helps us not guarantee, but get to the center of or the lowest point.
This line is always like a.
But yeah, here you can close this. But you saw like how it hit all those points, and it went there, and it makes like a really nice V. Now we're gonna show if we change this. Go back to the top. Let's change this to the learning rate we used, and let's do 5,000. Save, and now run it.
Okay.
So now we're doing it much faster. We're probably going to get a lot closer to 0. Hopefully it won't lag as much because there's not as many.
Wait, now we're actually, this loss function is better.
Yeah, because our learning rate is much higher. We're learning a lot faster, so we can do way less epochs than the other one.
Like, so technically we could have done 2,000 and reached similar result because it's 10 times faster learning rate.
Right. So yeah, 50,000 probably would have been great for the other one. Would have probably went into 0. As you can see, this is where we started off, and we took a giant step to like right here. And then the steps start getting smaller and slower because the slope isn't as big.
I see. Okay. What if I do like 0, 1 now? Do you think it'll work?
No, it'll blow up, but you can try it.
And maybe 500 steps.
Yeah. But it should just oscillate back and forth until you get not a number.
Oh, damn. Okay. Oh.
Yeah, see, yeah, not a number because the number just got so big because it just kept oscillating back and forth, larger and larger. If we go up at infinity, and then the number just keeps getting bigger.
Oh boy, reminds me of Foxtram off beta. Okay, so I think
that's pretty much everything I wanted to show you. Next week we'll go into, we won't like work our way through on paper like we did here, but we'll go into more details on how we would do something more complicated like this. It doesn't actually add that much more complexity. It's just a little bit more numbers to remember as we're like working our way through it. Right. And then on the next lesson, I think we'll do actually coding our own backpropagation gradient descent algorithm.
All right. So I'm excited.
But we did it by paper.
No, I think math checks out.
And I think it's really satisfying whenever you can do it on paper by hand and you're still getting the same thing as the computer. Because I feel like a lot of the times you're like, well, this cool, great machine learning library is probably doing something that like I don't really know about, but it
no,
was
we know.
just as
Now we
simple
know.
as that. Exactly.
No, it's amazing. Yeah. So thanks, Nick. So join us next week. I think next week, if you're interested in next week, I'm teaching you how to write your own Docker file the right way.
Nice. That's what I need.
Yeah. So join us next. So next Thursday we're not doing a stream because it's gonna be the 4th of July, and we're gonna do it the 3rd of July on a Wednesday at the same time. And yes, see you next time. And the next week, Nick is going to show us all cool things about AI things. So thanks for joining again today. And until next time.